welcome to Mathematics Tutorial Series, which is organized by Oromia Education Bureau. I am Dr. Garuma, and our today's topic is about limits. Before we dive into talking about limits, let me tell you some important relationship that always exists between mathematics and real life. As you know, for example, there is a topic about quadratic equations in mathematics that has a natural description of, for example, if you throw a ball into the air, the trajectory of the ball, that is the path on which the ball moves, was originally the subject of discussion by early mathematicians and physicists, and then they derived the quadratic equation from the very natural curve that an object which is thrown into the air follows. With a similar argument, in mathematics, most of the time, the concepts are derived from nature. And it turns out that, for example, if you wanted to find the area under a curve such as this one, you cannot directly do so, but nature doesn't always supply to us objects like triangles or some regular shaped bodies to find their areas. So early mathematicians have thought about how they could find the area under this kind of figure, for example, under this curve. If they want to find the area of this kind of regular shaped region, they thought to split up the region into multiple rectangles, and that was one of the concepts upon which limit has based. So although there are a lot of real-life problems that involve limits, in this section we will focus only on two major problems that paved a way for the development of calculus. One of which, as I have tried to mention, is about the area problem, and the second one is about the tangent problem, how to find the tangent of a curved line. For example, there is no formula for this kind of very irregular shaped figure if you wanted to find the area, but I have a well-defined formula for if I want to calculate the area for this kind of rectangle, and that is simply area is base times height. So what if I split up this region into multiple rectangles and then add up them, so that eventually the sum up of those rectangles would be equal to the area under the curve. That is the way the concept of limit has evolved through time. So let us see some of the notions of limit. What does it mean exactly? Before sophisticated mathematical tools were developed in the early days, like Archimedes, when they wanted to find the area under a curved figure, and other Greeks have managed the problem by inscribing polygons in the figure and circumscribing polygons above the figure, and then letting the number of sides of that polygon to increase, so that eventually the summing up of those inscribed or circumscribed figures would be equal to the area under that curve. Here is, for example, an inscribed triangle. Because the triangle is inside of this figure, it is called inscribed figure. In means is inscribed means is within something, and circumscribed triangle, because it is circumscribed means is something which is outside of it. So this is what is exactly meant by to inscribe and to circumscribe. So for example, if I wanted to find the area of this kind of circle, assume this moment that we don't have area for a circle. There is no formula for area of a circle. This is the way you have to assume, because I'm taking you back to few centuries back, whenever the mathematics is for the first time being developed. So mathematicians of the day, what they did is, for example, they inscribe a triangle within a circle, because triangle has only 3 sides. I called it A3. If I increase the number of sides to 4, that is, I will call it A4, and then to 5 sides, A5, and the way through to, for example, A12. And at this moment, the area which is left between this polygon, 12-sided polygon, and the circle is now approaching to each other. So But in this case, there are a lot of spaces which are left between the triangle and the circle. So in the limiting situation, when A is the area is given as the limit of that an whenever n approaches to infinity, as we go from 3 to 12, as you observe, the area which is left between the circle and the polygon is highly diminished. What if that polygon is, the number of sides is going to infinity? By then, the area of the polygon will be equal to area of that region, that is the circle. So this is the way the concept of limit is introduced. So with our original problem, that is how to find the area under this kind of curve. Even if in this particular lesson we are not going to do that, but in this case I want you to at least recognize what is meant by a limit and how do we start to find the area under a curve by splitting them up into several rectangles. So for example, in this case my rectangles have larger widths, but if I decrease these widths, if I make them narrower and increase their number, the area which are left between them will be diminished. So if I further split them into narrower rectangles, the sum of the area under those curves will fit up into the region, provided that the rectangles are narrower enough and consequently larger in number, so that they would finally fit into the region under that curve. This is a demonstration of that. For example, if I am interested to find the area under y is equal to x squared, if I split them up into larger rectangles, they would not exactly fit into the region, but the narrower the rectangles are, the more likely that they would fit into the region, and that is essentially what is meant by the limit. So, for example, which one do you think in these all cases that will represent the area under the curve more accurately? As I told you, the answer is always the more we make it narrower enough and consequently larger in number. Look at this simulation. Firstly, it started with larger rectangles. As time goes on, the number of rectangles are increasing and consequently larger in number, and finally they would fit into the region. Now they fit into the region. Look again, this simulation. It demonstrates what I have been talking about. So the second illustration, previously we have been talking about area as an illustration of limits. Second illustration is about tangent problem. Tangent of a straight line is very straightforward. It's simply the vertical increment divided by the horizontal increment, y2 minus y1 over x2 minus x1, written in that way mathematically. But what if I'm interested to find the slope of this kind of curve? It happens that the slope of this kind is like if I have x1 here, correspondingly I have f of x1. If I have x2 there, correspondingly I will have f of x2 here. But the slope cannot be now f of x2 minus f of x1 divided by this x2 minus x1. That slope would give me the slope of this straight line. The slope of a curve is not unique because at every point the curve has multiple slopes. At every point there is its own slope. So if I'm interested at least to find the slope of this particular point, the way I do is I want to fix this point, and on the way I have to move that. If I call this point P and that point Q, I wanted to move Q towards P by fixing P, so that when they are closer enough, this secant line would finally form a tangent line there, and the slope of that tangent line could be calculated. This is otherwise a secant line. So this is what I have been talking about. We move Q towards P. It means, for example, if I call this x, if this I call f of x, if I call this one x plus delta x, correspondingly there is f of x plus delta x. So the vertical increment divided by the horizontal increment would lead us to write this formula. provided that this delta x approaches to 0, this secant line would approach tangent line. By the way, the word secant means is derived from Latin word, means to cutting a curve at two different points, but tangent line cuts only at one point. So finally, the 2 points which were originally farther away would now become closer enough to each other, and by then the line which was already a secant, this one is a secant line, now becomes a tangent line as the 2 points approach to each other. And that is a kind of limit then, because limit is f of x plus delta x minus f of x divided by delta x as delta x approaches to 0. That is the way the early mathematicians have approached to find the slope of a curve which would otherwise be impossible, only because we have made the 2 points closer enough that now we are able to find its slope. This is a demonstration of what I have been talking about. Originally, the 2 points P and Q have started out a little farther away, but as they move towards each other, the secant line that would have cut that curve in 2 different points, as delta x is diminishing, this moment is simply becoming a tangent line. So what we did is we picked up 2 points P and Q, and then we brought them together. That line shows that we are moving Q towards P, and then finally what happens is the slope of that curve at that particular point will be equal to the slope of this tangent line at that same point P. So finally we started up with 2 problems. The first problem being the basic problem of differential calculus, which is the problem of tangents. And the other problem is the basic problem of integral calculus, which is about the problem of areas. As we summarize the 2 cases into one diagram here, if I'm given a certain random curve such as this one, like f of x, if I want to find the area under the curve, that will lead me to the development of integral calculus. If I'm interested to find the slope of that curve at a certain point by drawing a tangent line to it, that would lead me to what is called differential calculus. And this is the way calculus has been developed. So this brings us to the end of this lesson. Thank you very much, and have your time to exercise more on this.